All right, hi physics class, Mr. Mellinger. It's Wednesday, May the 13th, and this is your day 56 lesson of distance learning. So we are in the subject of waves this week and just going over basic wave terminology. And next week we'll cover specific types of waves and see some maybe interesting videos, do some projects like light waves, sound waves, things like that. So here was a summary of where we left off yesterday. The terminology to know is frequency. That's how many cycles of a wave pass a point each second, and that's called frequency. It's measured in a unit of measure called hertz. The period is the reciprocal of the frequency, and frequency asks how many cycles pass a point each second. Period asks the question, how long does it take a single cycle to pass the point? And the mathematics of that is shown down at the bottom of the page, so they're reciprocals of each other. Lambda is the wavelength. It's how far it is in a straight line from the crest or top of one wave to the crest of the next wave over. It's a straight line, and it's measured like any length or distance. It's measured in meters or millimeters or nanometers or some form of unit of measure of distance. And finally, the wave speed. Wave speed is the formula down below, and it is the wavelength times the frequency. And those equations at the bottom are really the only equations that we have in waves. So now we're ready to move on and continue with electromagnetic waves. So what is an electromagnetic wave? An electromagnetic wave is a type of transverse wave. So it is one of those roller coaster type waves. It's a type of transverse wave caused by atoms producing a wave that is part electrical and part magnetic. All of the energy we receive from the sun is in the form of electromagnetic waves. Therefore, electromagnetic waves include both light and heat. So all of the light we see, or even light we see that doesn't come from the sun, that comes from lights in the classroom, for example, are electromagnetic waves. Electromagnetic waves all travel at the speed of light in a vacuum. And a vacuum is a place where nothing exists, not even air. The speed of light is 300 million meters per second, or since it's a big number, we practiced some scientific notation when we were still in school, it's 3 times 10 to the 8th meters per second. And the speed of light is represented by the symbol lowercase c. So as I mentioned on the last video, light could travel around, at the speed of light, you could travel around the Earth 7.5 times in 1 second. That's the speed of light. Nothing in the universe, by the way, can move faster than the speed of light. It is the speed limit for the universe. Okay, so here is what's the relationship between wavelength and frequency in an electromagnetic wave. So when we talked about the wave speed equation, it was wave speed equals lambda times frequency, wavelength times frequency. But now if we're talking about electromagnetic waves, they all have the same speed, and that's the speed of light, which we use the symbol c. So there you see how we can rewrite this equation. Instead of writing V equals lambda times F, we can write C equals lambda times F, but that only applies to electromagnetic waves. So remember, all electromagnetic waves travel at 300 million meters per second in a vacuum. This means that the wavelength and frequency of an electromagnetic wave are related by the equation 3 times 10 to the 8th, or 300 million, equals lambda times frequency. So the speed is constant, but what can change is the wavelength and the frequency of the wave. And when you look at this equation, you just kind of want to notice that what happens is if the wavelength gets bigger, if the wavelength number gets bigger, in other words, you have a longer wavelength, then the frequency number has to get smaller. If the frequency gets higher or bigger, a bigger number, then the wavelength has to get smaller, because those two numbers multiplied together have to equal 3 times 10 to the 8th meters per second. So here's a simple problem down below. It's just another problem broken down for you. What is the frequency of a radio wave where lambda equals 1 meter? The wavelength is 1 meter. So you're looking for frequency. The velocity of the wave is the speed of light. Since it's a radio wave, that's a type of electromagnetic wave. And we're going to get into the types of electromagnetic waves that there are. And that's 3 times 10 to the 8th meters per second. And lambda gives you that is 1 meter. So solving the equation for F, you have In other words, you divide both sides by lambda, and you get frequency equals speed of light over wavelength. That would be 3 times 10 to the 8th over 1. And so that would be 3 times 10 to the 8th hertz. So it would have a frequency of 300 million cycles per second, or hertz. And generally, electromagnetic waves have very, very, very high frequencies, very short wavelengths and high frequencies. Okay, so this is called the electromagnetic spectrum. Let's go over what this is saying. What it is saying is that these are all the different types of electromagnetic waves that we get from the sun, and many of them we create on our own here on Earth. So way over on the right-hand side, we'll start on the right and move to the left. So you have radio waves, and those are the type of waves that are sent out by TV stations in the old-fashioned days. This is really the olden days, where those transmitters that you see up on top of mountains would send out radio waves. They have very long wavelengths and very low frequencies. And their wavelengths can actually even be, a mile long. Those have the least energy. So the lower the frequency, the less the energy of an electromagnetic wave. As you move to the left, you get a little bit higher energy wave. It's called infrared. Infra means below, and red means the color red. So we'll explain why it's called that in just a minute. But that has a little bit higher frequency and shorter wavelength than a radio wave. By the way, in between infrared and radio waves, which is not shown on this diagram, are microwaves. So you've all heard of microwaves. Those are in between infrared and radio waves. Now we move to the left and we get to the one that's really interesting. This is visible light. And you'll see that visible light is just that little sliver between ultraviolet and infrared. There are only certain wavelengths and frequencies of light that can actually stimulate our eyes so that we have a sensation of light and of color. And those fall into the visible light range. And as you can see, it's a very small range. What they've done is they've taken that little sliver in between ultraviolet and infrared, and they've gone down below, they've broken it out and expanded it out so you can actually see it. So you see that the light that is further to the right, that means it has the lowest energy, the lowest frequency, and the longest wavelength is red. And as you move across, over on the left, you get violet on the far left. And that's the side that has the highest frequency and the highest energy light. And in between you get all the other colors of the rainbow. So there's an expression, Roy G. Biv, but you have to say it backwards. So Roy, R-O-Y, is red, orange, yellow. G is green. You see green is in the middle of the spectrum. And Biv is B-I-V. So it's blue, indigo, and violet. So violet's furthest to the left, red's furthest to the right. Red is the lowest energy wavelength of light or color of light, and violet is the highest energy. Now if we go to the left past visible light, you see ultraviolet, and that's a higher energy light than visible light. So the name's infrared. Infrared means below red, so it means it's to the right or has a lower energy than red light, which you see down in the color spectrum down below. So it's to the right of red light. And ultra means above, so ultraviolet means it's above in energy violet light. So that's how ultraviolet and infrared get their names. Okay, so keep moving on, and we have X-rays. And X-rays are a higher energy than ultraviolet. That means they have a shorter wavelength and a higher frequency. And then finally, the highest are gamma rays. And gamma rays have the highest energy, the highest frequency, and the shortest wavelength. By the way, if you go down to the light, you see the scale down there. It looks like it goes from about 380 to about 740. If you look down at the very bottom, and those are nanometers. That's 1/1 billionth of a meter. So it's about 400 times 10 to the minus 9th. 10 to the minus 9th is a nanometer. So it's 400. So it's about 380 nanometers to about 740 nanometers, and those are kind of loose. Ranges. A loose range. It could be a little bit bigger than 740 and a little bit lower than 400, but it's approximately that. Okay, so that's the electromagnetic spectrum and the visible light spectrum down at the very bottom. So how does a wavelength of an electromagnetic wave affect it? There are 6 major kinds of electromagnetic waves that were shown on the last slide, from longest wavelength to lowest frequency. Excuse me, from longest wavelength and lowest frequency to shortest wavelength and highest frequency. So from longest wavelength, lowest frequency, and lowest energy, you have radio waves that are used by radio TV stations. Infrared. Now, infrared are put out by anything with heat. It's a kind of wavelength that's put out by something with heat. So when you see that the police or the military use night vision, and if you've ever seen that, it looks like it's all dark except a person or something that's warm, has kind of a ghost image to it. It's like white. It could be a vehicle, a tank. It could be a person's body. That's infrared. It works just like a regular camera, except it just receives and it senses a different wavelength of light and a different frequency of light. Infrared cameras do. Other than that, they work just like regular cameras. Visible light, we can see these with our eyes. Ultraviolet light, and sometimes people do art in ultraviolet light, so if you show it under ultraviolet light, you can see it. X-rays, that's what's used by doctors and dentists. The reason is, an X-ray can easily penetrate your skin, but it doesn't penetrate your teeth or your bones. So it leaves an image. And that's why doctors and dentists use X-rays. So it penetrates parts of your body, but not the bones, not the teeth. And finally, gamma rays. These are the highest energy wave. These will kill you if you're exposed to these too much, and they go all the way through your body. Okay, how are electric and magnetic fields related? An electromagnetic wave. In an electromagnetic wave, the electric part of the wave travels at right angles to the magnetic. So that wave is traveling to your right, and you can see that the electric field is going kind of up and down, and the magnetic field is going along with it, but side to side. So electromagnetic waves actually have an electrical part to them and a magnetic part to them. So here's a summary of the different kinds of waves. Transverse waves are the ones that move up and down like roller coasters. The most important type of transverse wave is the electromagnetic waves. Notice a transverse wave, you could go outside with a rope, and it's something that we would have done in class, and shake a rope up and down, have a friend hold one end and you hold the other. You shake it up and down. That would form a transverse wave. So that's a transverse wave is all. But the kind that we're really interested in here are electromagnetic waves. They're the most important kind. And then of electromagnetic waves, we have the 6 types of electromagnetic waves that we just talked about. On the other side, we have the longitudinal waves. Those are the kind that move back and forth. So that image you see up above where it looks kind of dark and kind of light and kind of dark, it looks like it's in bands. That's like a sound wave, and that's the air pressure. And what sound waves do, we'll talk about more of this later, is they squeeze the air together and then they release it, and they squeeze it and release it until finally the wave reaches inside of your ear, and that squeezing and releasing of the air will wiggle your eardrum, and that gives you the sensation of sound. We'll talk more about that later. But that's what that's representing. So it's a back and forth wave. It doesn't go up and down. It goes back and forth. So sound waves and springs are the most common kind of longitudinal wave. Okay, so I'm going to end this here. And I'll ask you some more questions. Tomorrow we'll go over different properties and different ways that waves work in different ways, and that'll be our last lecture for the week. Friday will be a work day. So go ahead and do this, complete the assignment, take a picture of it, email it to me, or put it through the Canvas site. I don't really care which, and just be sure it gets to me. And this is all due next Monday on May the 18th. All right, have a great day. We'll see you on Thursday, May the 14th.